for the talk. Thank you.
All right. Thanks a lot for having me here. It's a pleasure. And before starting, I would just like to say, if anyone has a question or anything related to the presentation or just a general question, please feel free to stop. You can. I'm not sure how it's moderated, so if you want, just unmute your mic and ask me a question. That should work. All right, let's start. So my talk is titled "Every cloud has an absorption feature." You'll see in a little bit why. Um, let's talk about this image right here. This depicts the history of the universe, basically, starting at the CMB all the way on the left and the modern day universe all the way on the right. Now, at this point, this image may not make sense to all of you, but I would like you to remember how the flow is going from the left to the right. Initially, you have a initially you have a fairly homogeneous medium, and you start seeing these bubbles that show up. And as time passes, these bubbles grow larger and larger. At one point, neighboring bubbles start to overlap, and as at one point, all of these bubbles overlap into a massive bubble that we call as the modern day universe. So I would like you to remember this particular image for the future slides. Before going into my research a little bit, I feel like I should give an introduction about myself. So as Kaustubh said, I graduated from IISER last year. I was in the batch of 2019. I'm a big fan of music, and I've played in a bunch of carvas. I like hiking. These are some of the hikes that I've done in the Bavarian Alps near Munich. One of my pet projects that I'm working on right now is visualization of data. So what I do is I simulate something and make these very nice looking images. For example, these are two very massive Milky Way-like galaxy clusters and their star densities projected onto a plane. One of my biggest activities that I absolutely adored for the last 5-6 years is Mimamsa, IISER Pune. I was in Mimamsa because of my cousin brother who got me into chemistry before I joined IISER. He's a year ahead of me. You guys might know him, Shreyas, some of you. You can take me out of Mimamsa, but you can't take Mimamsa out of me. Some of my best discussions and best fun moments from physics that I remember are from physics Mimamsa discussions. And a normal day in my life looks like this. I sit in front of a bunch of computer screens, write a bunch of code, and read a bunch of papers. So let's move on and talk about the history of the universe. Now, this illustration here very accurately describes the history of the universe at the CMB to the modern day universe. So the CMB, as we know, is the cosmic microwave background, which is the surface of the last scattering. And right after the CMB, the universe was a very, very cold and a very dark place, which means there were pretty much no sources of light. The only source of light was the fading glow of the cosmic microwave background. Now, gravity started doing its work during this period of time, and as collapse happened, your first stars and galaxies started to form. Once your first galaxies, sorry, did somebody say something? Okay, so as your first stars and galaxies started to form, they started producing radiation, and this radiation started to ionize the gas around it. Now, what was the gas around it? Throughout this period, the primary constituents of gas were hydrogen and helium. Hydrogen was the most abundant element, and the helium, which was the other one, are the primordial elements. When we refer to reionization in this case, I refer to reionization of hydrogen. There are reionizations of other elements, but that's a discussion for another day because those are very, very poorly understood so far. So whenever I say reionization, I mean reionization of hydrogen. So these first stars that formed produce UV ultraviolet radiation. And as we know, the ionization potential of hydrogen is 13.6 electron volts, which is right in the middle of your ultraviolet. So your first stars and galaxies are the ones that started this process of ionizing the neutral gas around them. And as time proceeded and more radiation was pumped into the intergalactic medium, you can see that the illustration from below now makes us a little bit more sense, where your radiation is being pumped in your surrounding gas. The surrounding gas is ionized. These pockets of ionized gas increase in size. they overlap, and roughly around redshift 6, the entire universe is completely ionized. Now, when we say completely ionized, what we mean is the ionization fraction of the universe is 10 to the minus 4. So there is one neutral hydrogen atom in, 10 to the 4 hydrogen atoms in total. This is a brief history of the universe, and the Epoch of Reionization, as we know it, is roughly the period between the formation of first stars, which is at redshift 30, to about redshift 6. And we have certain observational proof to show that reionization ended at roughly redshift 6. All right, so as I just described, this period was very, very important in the history of the universe because it saw the birth of the first stars, formation of the first metals in the life cycles of stars, and as well as formation of progenitors of these massive, massive galaxies such as Milky Way and Andromeda. And you can understand why the physics of reionization is so important because it promises to shed key questions like what were the first stars? How heavy were they? What were the first galaxies like? How did they evolve? Did sources like supermassive black holes have an impact on galaxy formation? Did reionization itself have an impact on galaxy formation, and so on? So understanding this period is very, very important to understanding modern day astrophysics and the local universe that we see around us. So the next question that you would ask is, how do we study it? How do we know that this is an epoch of reionization? So far, observationally, what we have done is we have observed quasar spectra. Just to be clear, a quasar is what we call a quasi-stellar object. And it's basically a galaxy with some sort of a supermassive black hole accreting gas at the center. And it basically emits a very, very large amount of light. It's a very, very luminous object. Quasars are quite rare to find in the early universe, but they are some of the most powerful probes of the early universe, just because how bright they are. High redshift galaxies are also another key probe. For example, galaxies, there's this class of galaxies called the Lyman alpha emitters, and these are galaxies which specially emit radiation in the Lyman alpha wavelength of hydrogen, which is basically the 2-to-1 transition of the hydrogen atom. The cosmic microwave background, as we discussed, is the surface of last scattering, which is the first light that free streamed through the universe, and the 21 centimeter line of neutral hydrogen. I'll discuss these in a little bit more depth in the following slides. Now, observationally, in the current day, which is in 2020, we do not have the best technological capabilities to probe very deep into the reionization epoch. At this point, we are very, very on the edge. So the deepest quasar that we have seen right now, the youngest one, is at redshift 7. And in the next decade, there are a bunch of telescopes, quite a few actually, that will come up and help us probe deeper into this epoch, which is a very, very important part of the history of the universe. Because of the the universe on computer simulations using prescriptions for gravity, prescriptions for evolution of gas, stellar life. And in the last year or so has turned out to be a very powerful probe to see the epoch of reionization. About the observational part of the EOR first, and let's start off with what we call the Lyman alpha forest. So the Lyman alpha, as we know, is an absorption line series of neutral hydrogen, which is the transition from 2 to 1, the second atomic level, to the first, and that's the Lyman alpha wavelength. Which is
Aniket.
Sorry, yeah, go ahead.
Yeah. So your voice was breaking a bit when you mentioned the point about computer simulations in the last slide. Maybe you can repeat that. There are a few messages in the chat about it.
Oh, I'm sorry. Give me a second.
Yeah. Just repeat that point. Yeah.
Yes, I will.
Thanks.
All right, so I'll repeat the part about computer simulations. So observations of reionization are quite limited at the moment because the telescopes that that are technologically capable are coming up in the next decade or so. So what we do is we have quite a good understanding of the cosmic microwave background thanks to satellites like Planck and COBE and WMAP. And we have some observational constraints from all of these observables from whatever current technology we have. What we do is we simulate the evolution of the universe starting from the cosmic microwave background or at a very high redshift using some sort of an initial condition that we have based off the Planck data. And we evolve this using prescriptions of gravity, prescriptions of gas evolution, prescriptions of stellar life cycles, and so on. And we evolve these all the way down to redshift 6, redshift 0, and so on, depending on the goal of the simulation. And we use these to model and study the reionization epoch, as well as to make predictions for these future telescopes that are coming up. So let's understand the first probe on the observational side. That is the Lyman alpha line of neutral hydrogen, which is the 2-to-1 transition at 1215 angstrom. And what you see here is a quasar absorption spectrum. If you have a quasar in space here, the light from it will travel through the intergalactic medium and reach the Earth and will produce some sort of a spectrum that looks like this. So your Lyman alpha, if your Lyman alpha line like this lies right here, what you see in this case right here, the blue color over here represents neutral hydrogen gas. The Lyman alpha line is extremely sensitive to neutral hydrogen gas, such that even if you have a neutral hydrogen fraction of 10 to the minus 5, you will see a complete absorption of whatever light there is. So as you can see, this trough right here, which corresponds to the size of the physical size of the neutral hydrogen gas there is. And this is named after the people who observed it first in 1965, called as Gunn and Peterson. And as you can see, as you move towards Earth, which is lower and lower in redshift, your neutral hydrogen content decreases, and you start seeing some of these absorption features, and instead of complete extinction. And this right here between the Lyman alpha line and the Lyman beta line is what we call as the Lyman alpha forest. Now, this is very important at low redshifts in the sense that between redshift 0 and 6, also just to give a timeline reference, redshift 6 is 1 billion years after the Big Bang, right here. So 6 is roughly 1 billion years after Big Bang. So just as a reference in time. So what this does for us is it does give us some insight into the epoch of reionization, because whenever you have neutral hydrogen, you see a complete extinction. Now, this is an example of a bunch of quasar spectra starting at redshift 5.7 all the way up to redshift 6. As you can see, all of them show a characteristic drop in flux on the left side of this point, which is the Lyman alpha line. So if you look at the blue-word spectra of these, as you move higher in redshift, you see that the troughs are getting larger and larger, and they are getting much more, flatter. What this indicates is, as you move higher in redshift, you do see an increase in the neutral hydrogen content. And numerous observations of quasars all the way from redshift 0 to whatever this is, redshift 6, have shown that there is a significant turnover point where this Gunn-Peterson trough starts appearing. And that point is very, very close to redshift 6, which is another observational proof of sorts that suggests that something happened at redshift 6, and suddenly there's hydrogen above. The hydrogen content of the universe increases beyond that point. So, and as you can see, there's another thing to look at. Not all of these spectra are completely flat. Some of them have these features. What this indicates is reionization is not homogeneous. Some lines of sight can have more hydrogen than others. So just using a simple quasar spectra, we get so much information out of it, that there is something happening at redshift 6 such that beyond it, your neutral hydrogen content increases. Now, and the fact that it's not homogeneous and it could be patchy, which is what we call as patchy reionization. Now, I would like you to note that the redshift 6 constraint is quite loose, and there have been debates about it. But it's the point of completion of reionization is somewhere around redshift 6, which is what I would like you to take away from this slide. The next observational probe is the cosmic microwave background. So as I mentioned earlier, when in the very, very early stages of the universe was extremely neutral. It was cold, which means there are no free electrons flying around. As reionization started and hydrogen started getting more and more ionized, it released more electrons into the IgM, which means your electron density increases as reionization proceeds. At the end of reionization, there is no more hydrogen to be ionized, which means your electron density from the end of reionization to the modern day universe, which is at redshift 0, is pretty much constant. Now, these CMB photons can scatter off electrons, which is called as Thomson scattering. If you take lines of sight to the CMB from the Earth, what you will see is that each line of sight will have an optical depth that we can define for the Thomson scattering process that happens of CMB photons. Now, what we can say is, but in this early part, when there were pretty much no electrons, your Thomson scattering optical depth will be pretty much non-existent. There is no scattering happening in this early universe. As for the late stages of the universe, beyond reionization epoch, your electron density is pretty much constant, which means your optical depth shouldn't change across lines of sight or across time. So we calculated the optical depth from the end of reionization to redshift 0, and that comes out to be a fixed value. Now all you need to do is calculate the total optical depth and substitute that into the integral value. This is a very strong probe because this gives us a bound on the reionization, which is the starting point and the end point. Now these bounds are loose, but it's still information that can be extracted. As well as the bounds, it also gives us a pretty decent constraint on the 50% mark of the reionization, which is the point where 50% of the universe was reionized. And from the latest satellite data, which is the Planck satellite, we get an estimate that reionization was 50% complete around redshift 7.8, which is a very nice estimate because that helps out simulations a lot. And in general gives us quite a bit of understanding of the reionization, because we can then define sources and evolve a universe such that we get a 50% mark over at redshift 7.8. So CMB also gives very, very valuable information about the reionization epoch. Now, going back to the quasar absorption lines that I was talking about earlier, these are very versatile because when you have light passing through a gas, it passes through a variety of scales. It passes through your interstellar gas, it passes through your intergalactic gas, which means it can give us information about a multitude of scales, which is very important because understanding processes on different scales is important for a complete description of reionization physics. And as I mentioned in this plot, Lyman alpha line saturates beyond redshift 6, which means we can barely get any information out of this. Or you could even go as far as saying that if you have a completely flat trough, all you can say is there is neutral hydrogen, but not much more than that. So Lyman alpha becomes pretty futile after a certain redshifts, and it's roughly around 6.5. But metals are very, very versatile, and metals can provide us a great alternative to the Lyman alpha forest. Going back to this spectrum right here, you see these absorption lines right here. These are most likely metal absorption lines, this one right here. And this hasn't extinct. This hasn't completely extinct. So you can isolate this and get a bunch of information about it. And this is what I mean when I say metals can be a great alternative. They are very versatile because they give us information about the local metallicity, your local star formation history, your local ionization equilibrium history, your local density, temperature, and so on. So metal lines can give you. Sorry.
So Agam has a question. Clarify what you mean by metals.
Okay, so I was going to get to that very soon, but when I say metals, I mean everything except hydrogen and helium. In astronomy, we refer to metals as everything except hydrogen and helium. Yes, we do refer to sodium, lithium, etc. as metals. Oxygen is a metal. So in this scenario, metals are everything except hydrogen and helium. And the good part about this is we have observed metals all the way up to redshift 7, which is well within the reionization epoch. And hence quasar absorption lines can be very, very important. All right, so the next important probe, which has become quite relevant in the last couple of decades, is the 21 centimeter line. It's a spin flip transistor of neutral hydrogen. Now we know that hydrogen has a proton and a neutron, and both of them have spins. When the spins are aligned, that configuration has a certain energy. When the spins are not aligned, that has a certain energy. And when either of the spins flip, that transition releases a photon at a wavelength of 21 centimeter. And this is very important. This is a very interesting probe because when you define an absorption line, you define its lifetime based on its Einstein coefficient, which is given by this number right here, A10. And this number for the 21 centimeter line is extremely small. It is 2 into 10 to the power minus 15, which means this hydrogen line is very, very, very weak. And it depends on the amount of neutral hydrogen there is for it to be seen. And luckily for us, the reionization epoch has a lot of neutral hydrogen. So that kind of works out. And the best part about this line is the optical depth is completely determined by these two numbers right here, which is the neutral hydrogen number density and the temperature of gas. All of these other things are constants. And so it's a very, very strong probe. And owing to its extremely weak nature, what it can do is it can map the tiny fluctuations in density, because you have a slight fluctuation, this value is linearly proportional to this. And if this varies, you can see the variation or the fluctuation in its optical depth. So 21 centimeter can be used to map these very, very tiny overdensity fluctuations, which are important because then you can probe very, very small scale sources. Now, another thing about 21 centimeter, how we use it is basically if you have a telescope, you have a gas cloud, you use something as a background. Now, classically, what people have done is used the cosmic microwave background as a background source. There is some absorption or emission for that matter. 21 centimeter can produce emission as well. And then you'll see some sort of a signal. But what if we replace the cosmic microwave background with a quasar? Now, what this assures us is that the quasar is always brighter than the gas, because this gas most likely is not as hot as this quasar. So what this assures us that we have a very, very bright background source. So basically, you're putting up a light bulb or a candle behind your gas cloud, and you're seeing that gas cloud in absorption. And that can reveal quite a bit of information. And these are the observational aspects of the epoch of reionization that are actively studied today. Let's get into the other side of things, which is the simulations. Now, there are multiple ways to do simulations. There are some very basic analytical ways, and then there are extremely expensive radiation hydrodynamics simulations. If you want very, very realistic, if you want very, very high resolution, accounting for a lot of physics, you go for these. But the problem is that these are so computationally expensive that these can take years to run. For example, I'll be describing a set of simulations that I used for my project, and they took almost 2 years to run. So there's a trade-off between how much realism you want and how much computational efficiency you want. What you can do is you can have very minimal set of physics and just make very, very massive sized boxes, as in very, very massive sized universes. These simulations are usually quite small. So you cannot probe very, very large scale properties using these simulations. But if you want to study, for example, the intergalactic medium, the interstellar medium, you usually use these high resolution simulations. I don't want to go into detail about each of them because, well, it needs it's unnecessary at this point. But the main difference between these two is the coupling. In the n-body plus radiation, what you do is you run the gas and dark matter separately, and then you run the radiation hydrodynamics as a post-processing step. Whereas in this, they are both coupled to each other, which means the evolution of radiation is kind of determined based on some properties, some assumptions. It's connected by some equations to the evolution of gas, and hence why it takes so much time and effort. So now that I have given you some basic introduction to what reionization is and how do we study it, I'll talk about what I do. What my group does is we use simulations of reionization to study certain properties of the IGM, to study certain galaxy properties, etc., and make observables for the future telescopes that are coming up. And in particular, what we have chosen is the 21 centimeter line and metals. And this is a very interesting study because they have some very specific synergies which can be exploited to get a very, very wide range of information about the underlying gas. And along with this, we will use this study to see if future telescopes can actually achieve this. There's no point in a study which your telescopes can't look at, right? So that is also another aspect that we look at. So before we move on, here's a nice reionization anecdote, which I would like you guys to read. All right, I hope you guys could get a glimpse of it. Otherwise, you can. I'll link it to you guys later on. All right, so these are the set of simulations that I used for my research. They are called the Aurora simulations, and these are the complete full suite of radiation hydrodynamics, which means they are quite expensive to run, and you have your gas and radiation evolution coupled by a certain set of equations. They are spatially adaptive, which means normally how simulations work is we set up a grid, and your your physical quantities like temperatures, gas pressures, densities, etc., are set to a grid. So every grid cell has a single value. Spatially adaptive means your particle is treated as a particle and not a set of particles inside a grid, which allows us for more resolution and more accurate results. It also treats feedbacks consistently. What I mean by this is, in real life, you have stellar life cycles, which means stars go boom. You have supernova feedback, you have your quasars, you have your supermassive black holes emitting a lot of radiation and pushing gas around inside of these local environments where they exist. And these Aurora simulations do track stellar feedback as well as supernova feedback quite well and self-consistently, which means we don't have to give up a separate prescription. It does things on its own. Along with that, because we wanted to study metals, these simulations also track the ejected mass of 11 metals, which basically means we track the evolution of stars, because star life cycles are what produce metals, including your AGB stars, your supernova, and so on. And just to make sure that these simulations don't give nonsensical results, these are calibrated to observables. For example, as I mentioned, the 50% deionization mark that we have, thanks to the Planck satellite, they are calibrated to this. These simulations produce 50% reionization at redshift of 7.96, which is very, very within the range set by Planck. So we also reproduce observables just to make sure that these make sense. And this is an example from the simulation itself. It's a slice inside of a box, as you can see. This shows the neutral hydrogen fraction. Your blue regions are extremely ionized, which means there is pretty much no neutral hydrogen. Your reddish orange ones are those which have a very high fraction of neutral hydrogen. What you can see is a zoom in area on the right side inside of a very highly ionized region, which shows how adaptive and how high resolution this simulation is. So inside of an ionized regions, we can resolve these tiny pockets of neutral gas as low as 30 kiloparsec. Now, just for your reference, this entire box size is about 50 megaparsec, and we resolve things down to about 30 kiloparsec. So this shows how high resolution simulations these are. To answer Agam's questions from earlier, what are these metals that we speak of? We are particularly interested in oxygen, carbon, silicon, and iron, mostly because they do agree very well with hydrogen. As you can see from here, oxygen has a ionization potential which is only 0.02 of hydrogen. So they can do this very nice thing where they exchange electrons and both of them manage to stay neutral within the same gas. Now, what this could suggest is oxygen could potentially be a tracer of hydrogen, which means wherever we find neutral hydrogen, we could find neutral I made a mistake there. Wherever we find neutral oxygen, we may find neutral hydrogen as well. And this is the beauty of using oxygen. Just to clarify things here, this notation right here is basically when I say C2, it means C plus 1. So whatever this Roman numeral is, subtract 1, and it's basically your element to the power that number. These metals are, and all of these metals have been shown to exist in neutral hydrogen, which is why we to trace hydrogen using metals. And what I would like to leave you with is a bunch of nice plots. This is again a slice through our simulation, which shows the evolution of a certain halo. Now, this is centered at the most massive gas halo, most overdense halo in the simulation, and its evolution through reionization. So you have at redshift 11.3 all the way down to redshift 6. The leftmost column shows the neutral hydrogen column density, and the rest of them show the metals indicated. As you can see, that hydrogen disappears by the end of reionization from the general universe. It does exist within these high density halos, and your metals trace it very well. Now, if you look a little bit deeper, you see that oxygen and iron traces hydrogen very, very closely, whereas carbon and silicon spreads out a little bit more. And this is what the goal was, to see if oxygen and hydrogen and the rest of these elements can be correlated. And just as a visual test, you do see that oxygen does somewhat trace neutral hydrogen. Now, what does this look like observationally? Because we can't see these nice slices observationally. This on its edge is about 4 megaparsec. Now, we can't see these massive slices using our telescopes. What we see is spectra. So if you have a telescope that can observe the 21 centimeter line, as well as metal absorption lines in reionization, what would it look like? These column densities, what we do is we project lines of sight through these, and we translate these column densities into absorption spectra using this equation right here for 21 centimeter. And what we get is a very nice result looking like this. So this one right here, the bottom part is at redshift 8, and this is at redshift 6. So as you can see at redshift 8, you have a nice looking 21 centimeter forest, and the blue lines represent the oxygen absorption. So you also see oxygen absorption in both of these plots. If you notice at redshift 8, I have plotted these red lines which show the coexistence of observers. So you have a black line overlapping a blue line. And this is important because this is exactly what we were looking for. Can one of them trace the other? So it looks like it can. And as you go lower in redshift, the only places hydrogen exists is where you see oxygen. And this is some, all right, that is a very strong statement to make, but you can find such cases where you have neutral hydrogen as well as 21 centimeter absorption. And these are some very special objects that we are still looking into. And this is the whole goal of our project, to show that we can correlate oxygen and 21 centimeter to a certain level of magnitude and use it to understand the epoch of reionization. Now, what information can we get out of this? As I said earlier, that the 21 centimeter line depends only on the hydrogen number density as well as the temperature. You can use the oxygen line to determine the temperature of the gas based on its shape. Substitute that temperature, you have your hydrogen content. So using them together has these very nice synergies that you can use. There's a wide range of uses, but this is the most important one that we are going for. And this has shown some promising results. All right. So before I move on further, I would like to stop here for a second because that was a lot of jargon maybe I threw at you guys. So if you have any questions, please go ahead and ask before I proceed. All right. So can I move on then?
In the diagram on the bottom, there are a lot of oxygen lines that don't have a corresponding 21
Yes.
centimeter line. Is there a reason for that?
Yeah, there could be multiple reasons for that. So hydrogen is very, very localized, as you can see from here, whereas metals do spread out through some cycles, like stellar feedbacks, stellar winds, and so on. So these could be places where metals have flown outside of the large-scale structure. These could be places right on top of a source of reionization. For example, you could have pretty much a star right there, which is producing these metals. And so when you have such luminous sources very, very close to the metal lines, they completely annihilate oxygen because they completely ionize them. So you won't see hydrogen. So there are multiple cases where hydrogen just doesn't exist. So yeah, so hydrogen just doesn't exist because of local phenomenon. And which is why characterizing these is quite hard, as you can see. Your point is excellent because there are oxygen cases where you don't see hydrogen. There are hydrogen cases where you don't see oxygen. And these are very special objects that need characterizing. And yeah, so these do lead to some interesting results. Does that answer your question? Or
Yeah, yeah.
all right, thanks. So what telescopes are we going to look at? The most important one for this study is the European Extremely Large Telescopes. Astronomers have this funny thing where they like to name their telescopes as stupidly as possible. So this is the Extremely Large Telescope. We already have a very large telescope, and there's another one in the works called as the Overwhelmingly Large Telescope. So I don't know what's next. If you guys can come up with a name, feel free to suggest. It most likely will be taken in. So this will primarily be observing in infrared. This telescope is the most important one to our study because it has the capability to look well into the reionization epoch, all the way up to redshifts of 8, 9, and so on in the infrared. Now, these telescopes, some of them are already active and some of them are still under construction. This one's coming up in 2025. It'll have its first light in 2025. At the moment, just this base concrete structure is built. There's nothing else built. The mirrors are being built elsewhere, but yeah, this is going to come up in the Atacama Desert in Chile. You have some radio telescopes like the SKA, which is still a project under construction. We have no idea when this will come up because funding issues. LOFAR and EDGES have already started operating, and they have already produced some very nice results. EDGES, was it a year ago, came up with a very controversial result, which is still under consideration. That could be a very, very nice and an important result if it gets approved or if it gets confirmed. Hera is another project which is dedicated to the Epoch of Reionization, and it should give us very nice results. Now, the JWST, which is set to launch in 2021, should also be important for the EOR community in general, but not as much to my project. But this is also a very important telescope, given that it actually takes off in 2021. It is said that it's going to go up on 31st October 2021, which means the launch will be probably in 2022. God knows. So as you can see, there's quite a few telescopes that are coming up in the next decade or so. And this is a very small list. There are a lot more. There are a couple other telescopes called DARE, which is the Dark Edges Explorer, and so on. So a lot of nice science to be done. And we are going to need a lot of people to do this, which is where you guys can get involved. There are a lot of nice projects coming up in the next few years, just when you will be, arriving in your 5th year, finishing up your 5th year, starting your PhDs and so on. All right, so that was a little bit of a summary about my research and some future prospects. Now, I didn't start in astrophysics right away. I went through a whole variety of topics. I had no idea in my second years what I wanted to do. And I started with StatMech, I went into condensed matter, then radio astronomy, and now I finally am in reionization. You guys might not know most of these, but I had a small project with Dr. Anil Gangal, who is now retired, in my 2nd semester. That's where I started. I basically wanted just to explore stuff. So I started off with StatMech. And from there, I had a very nice discussion, which was my first research-based discussion with a professor in IISER called, she's a group leader in HCross, Dr. Ashna Vajpayee. And I worked with her for almost a year in her lab, which was experimental condensed matter. I worked on superconductors. As you can see, this is a scanning electron microscopy image of the superconductor I made to test its purity. And well, unfortunately, it looks very, very unpure, and it was. And yeah, it was just a fun thing. As you can see the date, 7 July 2015. It was a very nice experience in my first year to get this done. It's just some experience in the lab. But eventually I found that this was not for me. I'm not a very lab-oriented person. And I met this PhD student in Shiv Sagar, Sri Krishna Shekhar, who helped me out with radio astronomy. And eventually I got to working with his boss, who is Ramanathreya, who you guys might have heard from the talk he gave last week. I worked with Ramanathreya for almost a year and a half. And I worked on this project called Double Double Radio Galaxies, which is basically using GMRT data to study galaxies which have 4 radio lobes, as you can see from this image. And if you attended Ramanathreya's talk from last week, he did mention that the GMRT is an extremely extremely noisy telescope, thanks to all the radio stations, roads, sugarcane mills, and whatnot around the antennae. This image on the left you see is after almost 3.5, 4 days of noise reduction, calibration, analysis, and so on. So this image you get after almost 4 days of analysis. And you see how bad it is. You see all sorts of fringy patterns, the sources are distorted, and so on. What me and Sri Krishna did was we came up with this pipeline. He guided me. He was my PhD supervisor. I was just a puppet doing some stuff. I had some ideas. And we wrote this pipeline to data analysis, which produced this very nice image, which had a noise of a few hundred microjansky, which was close to the thermal limit. So we were extremely happy with our results. We produced some very high resolution images of about 7 double radio galaxies and produced spectral dict maps and so on. And once I finished this, I started exploring a little bit more, thanks to, again, Ramanathraya, who encouraged me to look into places. And I was fortunate enough to get selected for an internship at the Max Planck Institute for Astrophysics, where I started working on computational cosmology. And I've been working with my current supervisor, Dr. Benedetta Chiari, for almost 3 years now. I did my 5th year with her. I'm about to start my PhD with her. I'm currently not in Germany. I will be there soon, but that's the project-wise journey from start of IISER to my PhD. Now,
Aniket?
Yes, go ahead.
Can you go back to the previous slide?
Yes.
So, what exactly do you mean by double radio galaxy?
Oh, right. Sorry. So you see this object right here, right? This tiny pixel at the center. This is a symmetric object. So if you take the one pixel at the center, that's actually the galaxy. And then you see these inside. You see these two blobs. Those are the inner lobes, and these outside plumes are the outer lobes. So when you have a quasar which is emitting jets, there's a supermassive black hole which is accreting mass, and it's emitting jets in both directions. What happens is these jets produce radio lobes like these, which is basically gas and matter which goes outwards in space perpendicular to the galaxy plane. What happens in some galaxies is the jets stop for some reason. And when the jet stops, these lobes, they go outwards and outwards because they have momentum. And they keep pushing outwards until they die. Basically, what I mean by die is they radiate away all their energy. And at some point, this jet restarts. So what happens is you have these outer lobes, and then because of the newer jets, you have these inner lobes that are forming. So what you see is this magnificent, mind-blowing structure of 4 lobes from a single tiny galaxy. You can't even see this galaxy. This object in its entire size is about a megaparsec in size. And the galaxy is how much? 20 to 100 20 to 100 parsec. So you can just imagine the scale and the violent phenomenon that's going on. It's basically a jet that is emitting gas. It stops and then starts again.
Aniket?
Yes.
So the outer lobes are again reignited because of the jets? Like
no. Outer lobes are dead. So these
but then you
inner
see
lobes...
them...
It depends on how old outer lobes are. So if your inner lobes start very, very soon, then the inner lobes pretty much like power through the outer lobe, right? At one point. So in that case, there can be re-energization. Sorry, there can be some sort of a re-energizing process.
Okay.
But for most parts, the activity stops for a few billion years. So these outer lobes go so far out that before the inner lobes reach them, they are pretty much dead. It's just dead plasma hanging around in space.
Okay.
Yeah. So if the period of the jet is small enough, then as you said, they can be re-energized. In fact, there is this thing called as X-rays, X double radio galaxies, where the plane of the jet changes, and then there's some sort of a re-energization happening. So Agam, this top one right here and this bottom one right here are the outer ones. And in this inner structure, you see it's like an 8 shape. So the upper one is 1, the lower one is 1. And in the middle of all of that, there's a galaxy sitting around. You obviously can't see the galaxy because of all of that. But yeah. These form some of the most spectacular objects. They are megaparsec sized, they are huge. And for a jet to push gas out to megaparsec scales twice, just think about how active and how violent that galaxy itself is. It's amazing. There's a there's a paper by Joydeep Bakchi from IUCA about one of these galaxies, and they found the optical equivalent of this. So they saw the radio double and they found the optical. It turns out to be a very violent spiral. If you want to look it up, it's a very nice galaxy. Quite remarkable how amazing these objects are.
So I had another question.
Yes, go ahead.
In this galaxy, is it faint or just because the clouds, not the clouds, the jets are so luminous that the galaxy is hidden?
Well, the galaxy is just too small to be seen. We don't resolve it.
Oh, it's not resolved. Okay.
It's an AGN. It's an active galactic nucleus, which means there's a supermassive black hole accreting gas. So it's going to be very, very bright in some other radiation. For example, if you see it in optical or infrared, you'll see it very bright. But unfortunately, in radio, it's just the scales are very, very off. You won't resolve it.
Okay, thanks.
No, I mean, I hope you can imagine it. It's just a tiny pixel at the center. It's quite impossible to see it. Yeah. I mean, yeah, you don't know if the galaxy is luminous enough or not, just looking at this image. It's just that we don't resolve it.
Okay.
Yeah. All right. So moving on. So how can you get started with astrophysics or radio astronomy and so on? So as I did, don't be afraid to explore, because even after you finish your fifth year, even after you finish your PhD, you can change subjects or you can change subfields. It's not that big a deal. All you need is, just love it. As I moved along quite a bit, and I found it quite interesting to explore. So keep exploring, find your interest, find where you find where you're most comfortable. I find that computational physics is where I'm most comfortable. Unfortunately, in astronomy, except I'm not sure how much instrumentation needs coding and all that. Maybe Sujay can shed some light. But almost every form of astronomy, astrophysics needs coding, and so you must start learning some sort of Python, Julia. Julia is a very modern language, and I would definitely recommend it. It's super fast, very easy to learn. You might as well learn C and so on, but those are kind of outdated now. And don't be afraid to start working on ideas of your own. You don't always need a professor to try something. For example, in my third year, I found this code called Gadget, which is basically the code used to run these massive cosmological simulations. And I found it I installed it on a laptop.
Aniket, your voice is breaking a bit. Sorry. It's still breaking.
Hello, can you hear me?
Yes, now we can hear. Can you repeat the gadget part?
Yeah, so there's this code called Gadget, which is basically used to simulate cosmological simulations for dark matter and gas and so on. For example, this image you see can be made using Gadget. So in my third year, what I did was I decided to download this Gadget, found a recipe to run it. So basically, all I was doing was following instructions, and I ran it on my laptop. Now my laptop is not very good, so my laptop was frozen for almost 6.5 days. But the end product was exactly this image, and that gives a lot of satisfaction, and you learn something new. So don't be afraid to start. If you have an idea, if you see something online, if you see something in a course, there are more than enough sources of open data online. For example, the Sloan Digital Sky Survey, that's a galaxy survey. The TNG simulations, which are galaxy formation simulations. You have all sorts of resources online. You just have to look for them. And get involved in projects. Look for active projects with professors. Find your colleagues, discuss things, ask your seniors, and so on. If you guys need any help getting into specific channels, etc., feel free to contact me. I would be more than happy to direct you into the right resources and so on. But at some point you have to just start exploring, and that's how you get started. Speaking of computing, as I am in a computing field, there was a very interesting recent paper which came out just 15 days ago on the environmental costs of high performance computing. HPC basically means high performance computing, which is what we do: simulations, running these massive data sets, running predictions, and so on. The environmental impact of this is quite a lot. And as scientists, it kind of comes down to us to kickstart the campaign to move towards greener and cleaner sources, to protect our planet. Now, this is a study done by the institute called MPIA, which is the Max Planck Institute for Astronomy in Heidelberg, and in coordination with one of the observatories in Australia on their carbon budget per researcher per year. And what they concluded basically was that electricity and flights are the most expensive ones, and they depend on your location. For example, Germany has very clean electricity that comes from renewable sources and so on, which is why their contribution from electricity is quite low. Whereas Australia has very, very dirty electricity, comes from coal and non-renewable sources, which pollute a lot, and hence their cost is so high. Flights is always a thing because researchers like to travel. Most of these conferences, as Sujay can attest, are in exotic locations in some corner of the earth, where researchers basically go on holiday and have 3-hour lectures a day. It's very nice, but it does need a lot of flights and so on, which does spend a lot of carbon. And the conclusion of this paper basically was that it depends on how clean your electricity is. I tried to look up this number for India, but I couldn't. I didn't find it. There were a lot of debatable sources and numbers, but it would be nice to find out what this is. And I know IISER has installed some solar panels, but obviously they are not enough. There are definitely more cleaner pathways to get these emissions to decrease from electricity itself. Just think about how much electricity the supercomputer in IISER uses, which comes from, say, coal sources and so on. And these investments, again, the same paper did make a point that most of these investments will make their returns within the next 5 to 10 years, which is quite quick. And reduction of air travel, which thanks to COVID has reduced by quite a bit. And there was another paper which did somebody have a question?
There's a question in the chat.
Yes.
By Abhinav, so he's asking what is TCO2e?
Oh, total carbon to emission per researcher. That's it. And there was this another paper which quantifies the high computing based on your observatories, the codes you used. Is it a CPU based or a GPU based? What they found was that GPU based codes are much more efficient and less stressful in terms of carbon to production. And Python is a very, very sad discovery that Python, because it's an interpreted language, does consume the most carbon when running a code. But obviously we can't stop using Python. It's a very important part of this. And what you do with this is then use things like Numba, Cython, and Julia, as I mentioned earlier, because they make your Python much faster. They make your Python parallel and GPU compatible, and hence reducing your carbon output. Now, obviously, these are not easy things to be done, but let's start a pathway towards cleaner and cleaner computing. And there is this another thing called as scientific conduct, spelled that way, which encourages people to report their carbon production per project per year and so on. It's a framework that is being developed. All of this is in very, very early, and it's in its infancy. As I said, the papers only came out about 15 days and a week ago, so it's just a nice thing to spread awareness about, and let's make our computing cleaner. Thank you. If you have questions, please go ahead.
Aniket, people are asking in the chat box, can you please share the links of these resources?
Sure.
Great, thanks.
Yes, give me a second, please.
Yeah, in the meanwhile, I would like to thank Aniket for the really amazing talk. It was very interesting, and especially your journey through IISER was very, amazing. That you started with such a different branch and you found your way to your interests, and that's inspiring. Thank you. Now I would like to encourage people to ask questions.
So here are the links for the Nature papers that came out and scientific conduct. All right, there we go. So those are the links. Feel free to have a look. Abhinav, I'll have to recheck that. Maybe it's tons, yeah. It could very well be. Yeah, it could be that. I've linked the paper if you want. I mean, apologies if I'm wrong, but you should you could go through it, I guess.
Okay.
As for Deep Jyoti, I mean, my supervisor is well. She has some very nice research, so I basically read her research and I emailed her asking, well, your research is very nice. I would like to work on this, and do you have a project for me? That's all it was. This was in 2017, the end of my third year summer. There was no application process. I just applied to her. CPI requirement. Does CPI mean GPA? Is that it? I'm sorry, what does CPI mean there? If it's GPA, there was no GPA requirement. My funding is done through the institute, and Max Planck used, at least my institute used to take summer interns, but they've stopped since like 2018. There are a few other Max Plancks which do take summer interns. There you should check out their web pages. My particular Max Planck has stopped taking interns since 2018. All right. Any other questions? I hope I answered those.
I had a question regarding the internship. You did an internship in Max Planck, right?
Yes.
That was in your which year?
End of my third year. So the summer after my third year, before my fourth year started.
So how do you apply to internships abroad? Is there a specific procedure depending on the institute?
So since I have left, I am quite sure that IISER itself has set up some very nice and easy pathways through, I forget the international officer's name. There is an international office that is set up, right? So they do have their MOUs and so on, internships. So you should look into that. They'll probably email you sometime soon. But yeah, IISER has some quite nice, quite a lot actually, with a lot of institutes. They've set it up in the US, in Europe, in Australia, and so on, in Israel, at the Weizmann Institute. So you should, Naresh Sharma or something his name was, I don't remember.
Okay,
The
that's nice.
international officer in IISER, yes. So you should contact him. And there are quite a few programs internationally, like, scholarships like the DART scholarship, the Charpak scholarship, the Essenbo scholarship for your internships. If not, what I did was I basically found my supervisor, and I loved her research. I wanted to work on that. So I emailed her just straight up, like, hi, I've read your research. I would like to discuss stuff, and if you have a project, and so on. That's it.
Agam has a question in the chat. So he's asking, how is life there? Did you come across any racism while there against you or any other case you know?
How is life there? I mean, in the institute, it's nice. We have some very, very big names in the institute. If you heard of Rashid Sunayev, Simon White, Volker Schwingel. So it's very intimidating, but it's great because discussions are just next level. It's a very nice environment to do research. My supervisor is amazing, so I'm lucky to have her as my supervisor. Did you come across any racism? No. At the institute, not even slightly. I've met some very nice people there. Outside institute, not really. I mean, in Germany, I haven't seen any racist incidents against me. I haven't heard of anybody else either. All right, if you have any other questions, please feel free to ask. Anything is cool. Yeah, I mean, it depends on what city you're in. I'm unfortunately in Munich, which is extremely expensive. It's probably the most expensive city in Germany. But yeah, it is enough. It's usually enough. I don't know about France. Maybe Sujay can answer.
It's you usually get funding based on your city. It's usually they compensate for the cost of living in the country and in the city.
Oh, okay. They don't do that in Germany. It's a fixed scale. It usually is enough, though. Don't worry about it.
Yeah, so sometimes when you email profs saying that you're interested in what they're working on, they typically ghost you. So what do we do in those circumstances?
I mean, profs mostly ghost you when they are super busy, or you know, or or you haven't. They don't see the interest that you show in them. It's one of those. So if a prof ghosts you more than a couple of times, you just have to move on. You can't keep bugging them. Profs are very busy, and my prof told me that she gets about 6-7 emails a week about internships. So that's pretty much why they ghost. So they look at candidates who have shown interest, so on. So I mean, if they ghost you, you'll always find people you're interested in working in. There's no point in getting disheartened and sticking to one.
So what exactly do they look for to say that okay, fine, this person is really interested in what I'm working on? There should be some sort of way to figure out what they are thinking of, right?
I mean, I guess you should probably have read their research. So they should see that they are not just emailing you. For example, there was this guy in IISER from Bhavesh's batch. That's 5th year right now, I guess. He emailed all the profs in IISER saying, "Dear sir, I want a project," and he CC'd all of them in the same email. Now that's not good, is it? So it's mostly it's just that they need to you need to read their research, and in your email should be good enough to convince them that you've read their research and you actually are interested in it.
Okay.
Or you could just ask for a call, because when they call you and when they talk to you, it's pretty apparent. Most of the profs, if they are interested in you, they will ask you for a Skype call or Zoom call anyway. But yeah, that's a step further. Just don't write a generic email. That's the worst. How do you contact me? My email. I'll put in my email. I mean, Facebook is fine as well if you're on Facebook. Yeah, that's my email if you want to contact me. Yes, I'm doing my PhD with the same prof. I did my internship, my 5th year, and my PhD with the same professor.
If you don't mind, can you go back to the last slide?
Which was?
I don't
Just give me a
remember.
second. I'll reopen the presentation. I'll share it. 1 second. Yeah, is this one?
I cannot. Oh, okay. Hi, yeah, this one.
Okay.
So in this, there are like 3 straight lines, and one of these lines is the bubble one is a curve, and it's cutting across them. So what is this line? I don't understand that.
Which one? The one cutting across?
Yeah.
So when you all right, so there's this thing. Are you aware of parallel computing? So if you have a code, you can run the same code on different n number of cores. So your CPU has a certain number of cores, right? For example, if you have an Intel i7, that can have 4, 8, 16 cores, whatever. So what you can, when you run parallel computing, what you do is you either share a task with these 16 cores, which means there are 16 cores doing the task at the same time, or so on. Or what you can do is each core does a separate task, which basically is called as parallel computing. And they increase the speed of on a very basic level, it's called parallel computing. It increases your speed quite a bit. So that line basically depicts the number of cores. So the rightmost is 1 core, the top is 10 to the 6 cores, is it? Yeah, 10 to the 6 cores.
Okay, so the more like the less cores you have, the less CO2 you produce, but like the faster solution you get. Oh, sorry,
No,
slower solution you get.
slow. Yeah, exactly. So it's like a trade-off.
It's like a trade-off here. Okay, thanks.
Yep. Do you have a social life in Germany? Uh, well, I can only speak about this based off for how my fifth year. I'm not in Germany right now, so I can't speak about how it is right now. But my experience from last year was basically, well, you go to work at what 9:30, come back home around 6, cook dinners, so on, work, sleep. Weekends are much more chill because, well, in Europe in general, weekends are supposed to be chill. If you choose to work, you choose to work. Otherwise, on weekends, it's mostly hiking, you know, go out, go out to a restaurant, chill out, so on. Yeah, that's it. That's a pretty decent work-life balance. You don't have to worry about it. At the end of the day, it comes down to you how much you want to work. PhD can be isolating, yes. I am not sure because, well, I'm not there yet. From what I've heard from people, I mean, it's usually just chilling out on weekends. Weekdays are mostly work, 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 work. I guess, I don't know, PS Sujay, do you have anything to say about this? You're pretty much finishing.
It depends, as you said, on the what you want to do. I mean, how your personality is. It depends. I mean, you can always find people like you for most of the time.
Thank you.
Agam has a question.
Uh, there's no clubs. I mean, so my institute at least had this thing called as weekly after work beers on Fridays, starting 6 o'clock. So people from all over the institute just come and chill out, drink beers and stuff. And weekends is usually for for hiking. Most of the people I knew did come cycling to work anyway. So most of them are very good cyclers there. I know quite a few people who cycle like 20 kilometers to come to work. What languages do I work on? Sorry, I personally use Python with Numba or Julia. Numba makes Python like significantly faster because it takes away the interpreted part of Python. It converts it to a compiled language, kind of.
How is no Julia user support? I mean, it's very new, so
It's
do you
very
find
nice. It's good. It's good.
so
At
if you
least recently, it's getting much better.
okay, so if you
Have you
find
heard? Have you
do you
heard of the
find like
YT project? Sorry. Go ahead.
sorry, what project?
YT.
No.
It's a basically like a simulation analysis and visualization software which is made for any sort of simulation data. Even people in like aerospace, biology, and whatever, you can use it on pretty much any simulation data. And that is quite I think that's a lot of it is written in Julia, so they are definitely increasing support. Yeah, and it did come out of beta recently.
YT project, you see. Okay.
Yes.
Okay, I found something. Okay, but so is it like Julia is like, are there people using in Astro community now? Like, because I usually like stuff to Python, but like, is it
Quite
very
a few,
different?
yes.
Okay.
At least in these simulation based people, they like using YT quite a bit. Sorry, Julia quite a bit.
Okay.
At least
Okay.
it's a very recent trend, I should say. It was
Yeah. I mean,
it was
Julia is 4 year, 5 year old. I don't know, like.
yeah, it wasn't like this like a year ago, but Julia is like gaining support quite a bit, especially after the recent NumPy disaster.
Oh yeah. Okay. Yes. That's what I saw. But for data analysis, I think there is no alternative than Python at the moment. I think
No. I mean, you can go for R and all, but
no.
R, sad.
No.
What is the NumPy disaster?
Google it. I mean, yeah, just Google
Okay.
it. No, but Julia is getting the NumPy is getting. What am I saying? Julia is getting much and much better. I lose my English skills at the end of a talk. My bad. It should be much better soon because the latest stable release was literally like 10-15 days ago, as far as I remember.
Okay.
I've used Julia a bit and it's quite nice.
Okay.
I mean, of course, most of my coding is done in Python using NumPy or like Cython, but Julia, I'm definitely considering moving on to Julia for some of my codes. Clarify. No, these are all pre-built. So as I said, there's this code called Gadget. That's used for running simulations, and people have modified it further and further and further. You don't have to start from scratch. All you have to do is set up initial conditions, set your run parameters, set up what physics you want to include, and start a run. You don't have to write everything from scratch. It's just you have to customize it to what you want. And some people write physics prescriptions from scratch. For example, I mentioned this simulation project called Illustrious TNG. What they did was they overhauled some of their galaxy formation physics to get more accurate results using a prescription from the older TNG, Illustrious results. So you don't exactly rewrite stuff. There are quite a few simulation bases. The most famous ones are Gadget, Gizmo, Enzo. I'm not sure if Enzo and Ramses is the same, but Enzo and Ramses. So there's quite a bit. Some of them are AMR, some of them are particle based, some of them are grid based. So it depends on what kind you want. Yeah, basically not from scratch. There are quite robust bases to start from.
Okay, so we are well over 1 hour. So if people don't have any more questions, I'll stop the recording here and end the talk here officially. People can stick around to have a chat with Aniket and all the other seniors, very nice alumni we have here. So I'll stop the recording here if people don't have any more questions. Thank you.
Thanks.